All right, so now we're on to application problems. So the first one here is on the senior population. So it says U.S. Bureau of Census prediction for the percentage of the population 65 years and older can be modeled as, and then it gives us this cubic function as a percent, where X is the number of years since 2000 and a date is from 0 to 2050 basically. So we're supposed to determine the year between 2000 and 2050 in which the percentage is predicted to be increasing most rapidly, and the percentage at that time, and then the rate of change of the percentage at that time. All right. So what we're going to look for is we're going to have to find the second derivative of x, set that equal to 0, and get our x out. Then we're going to plug that x back into f and get our inflection point, and we're going to plug it back into our first derivative and get our rate of change. Okay. So that's going to be the two items we will get. And then we're supposed to do part A for the most rapid decrease. So this is for both the most rapid increase as well as the most rapid decrease. And probably what's going to happen is we're going to do both of these along the same time. And that's going to be how it works. I'm thinking maybe. We'll see though. All right, so what we need to do is find p prime of x and p double prime of x, first and second derivative. So now we're going to take and multiply here. So 3 times that's going to give us a negative 0.00066x squared plus 0.028x minus 0.0033. Okay, and that's going to be percent per year. Okay. Now, what we need to do is take the second derivative. So that's going to be a minus 0.00132x plus 0.028. Well, that wrote that totally wrong. My pen doesn't want to do it. 028. Okay. And the x drops, we don't have that. And that's going to be percent per year per year. Oh, per year, not percent. Okay. All right. And so what we need to do now is we need to solve this basically for x. Well, this is only going to give us 1x. And so that's going to be a key kind of a item here. That's only giving us 1x. And so if we set that equal to 0, we get 0.00132x equals 0.028. Divide by that. And if I plug that in a calculator, 0.028 divided by 0.00132, I get 21.212121. So x equals 21.212121, and so on. Okay. Now determine the year between there and there. Okay. Well, the year is going to be year after uh, 2021 because this should be 2021. I'm thinking here, but if that's beginning 21 years after that, it, this could tell us it's 2021, and this could say it's in the next month, so it'd be 2022 actually. And so that's going to be a key here. I'm going to go check out the book here and look at that, how it really is looking here. All right, so yeah, so it says it was for that year. And if we want to know the month, then we're going to take that 0.212121 times 12. It's 2.5, and so then that would be March of 2021. Now, with that, what do we want to do? Well, we need to find P, or yeah, P, I guess we're not using F's, but we're using P's. So we're going to find uh, P of 21, 21, 21, and we're going to find P prime of 21.2121. Okay. And so that's going to give us basically our amount that is changing the most by and also that rate of change. And so if we plug those in, we'll take negative 0.00022 times 21.2121 to the third, and then plus 0.014 times 21.2121 squared minus 0.0033 times 21.2121 and then plus 12.236. And we get with that one 16.366%. Okay. And so that's going to be the percent that it's increasing the most rapidly in March 2021. Now we need to know that rate of change, and so we plug that into the first derivative formula. So now we'll take a negative 0.00066 times 21.2121, and that's squared, and then plus 0.028 times 21.2121, and then minus 0.0033, and we get 0.294 if we round it, and that's going to be percent per year. Okay. And so that's going to be our inflection point for the increasing side. Now the key is we only have that one point. And so what we're going to have to do is we're going to have to graph this. So I probably should have just did the graphing because I wasn't paying attention. And we're going to actually have to plug in, okay, we're going to have to plug in our original function and then take the derivative of it and actually find that. So minus 0.00022 x to the third, and then plus 0.014 x squared minus 0.0033x plus 12.236. And then I'm going to say, okay, well, we already know how the derivative is, but let's show that we can just get the derivative this way and graph it. And we'll say that's going to be from y1, and we want to take it with respect to x. And so our window, well, let's see what it looks like if we're going to be where close we need to be. And we need to actually go out to 50 here. And we only want 0 here. And so that would be what we're looking for. So we don't have to go down as far, but we need to go up higher. So maybe we can go to -4, but we can go up to 30. And so let's see what that looks like. Yeah, now we got everything in there. But we really need to look at this derivative graph because that's where the rate of change is. And they say they want the biggest rate of change. So that's our graph we found. So this is going to be kind of like the max. So that's going to be a 0 right here. This is probably going to have a curve here coming here. So around wherever that's going to be a 0. But what we need to do is we need to really zoom this in to look at our endpoints. So let's maybe go from -4 to 4 and go to 1 and see, because we want this piece here is what we want. All right, so that's increasing, increasing, decreasing, decreasing. So that looks to be the biggest decreasing point here. So let's see, that should be just 50 because that's where our point is. And so what we need to do then is we also need to find P of 50 and P prime of 50 to see where it's decreasing the most rapidly. So this is for decreasing, and this was increasing. Okay, so now we're kind of doing part B here. And so we're going to plug all those back into our function. Now, if we do that, we might be able to just plug it in here, do our second trace value, and we want 50. And so that's going to be 19.571 for our original graph and negative 0.253 for our other one. So that was really quick. So that was 19.571%, and this is a negative 0.253% per year. Okay. And so that was the two things we needed. We needed this, and we needed this basically. So those were the two basically items we needed. We just found the first and second derivatives, solved our second derivative for 0, and then plugged it all back in and got our values. Okay. And I guess I didn't need that extra page on this one, but I did need it on the one previous. All right. So let's pause there and then we'll come back with this one.